Hello, my name is Hwan Kim, and I'm going to present about the paper Momentum Contrast for Unsupervised Visual Representation Learning. The presentation will be presented in the following order. The overall sequence will mostly follow the original paper. First, we are going to overview what they propose to do in the paper. Momentum contrast, as known as MoCo, is an unsupervised visual representation learning method, so its purpose is to learn the encoder to make a good representation features. It is still considered as a baseline for many constructive learning and representation learning works. MoCo uses a dictionary that pairs a queue of keys with a momentum updated encoder to build large and consistent dictionaries and learns transferable features. Self-supervised learning is a training paradigm in which a model creates and uses its own labels derived from the raw data to learn useful representations without any human-provided annotations. It is a small subset of unsupervised learning. Representation learning usually compresses raw data into a compact vector that gives the important structure. Pretext tasks can be viewed as what is solved only for the purpose of learning a good data representation. After the pretext task is trained, the model can be used in more useful tasks like classification. For example, in autoencoder, it compressed the image and reconstructed it by minimizing reconstruction loss in a pretext task phase, and the frozen encoder can be used to train a classification task. Contrastive learning is a deep learning technique used for learning representations of data, which trains a model to bring representations of similar or positive pairs closer together while pushing representations of dissimilar or negative pairs further apart. Contrastive loss is the objective function that quantitatively enforces this by minimizing the distance between positives and maximizing the distance within negatives during training. MoCo can be thought of as a general mechanism for using contrastive losses. In the first figure, the encoders for computing the query and key representations are updated end-to-end by backpropagation. In second one, the key representations are sampled from a memory bank which consists of the representations of all samples in the dataset. In MoCo, it encodes keys from recent mini-batches, decoupling dictionary size from GPU memory. Using a queue can make the dictionary large, but it also makes it intractable to update the key encoder by backpropagation. They hypothesize that this is caused by the rapidly changing encoder with low key representations consistency. They propose a momentum update to address this issue. Moreover, what they discovered was that the model appears to cheat the pretext task and easily finds a low-loss solution because the intra-batch communication among samples caused by batch normalization leaks information. So, they used shuffling batch normalization, which trained with multiple GPUs and performed batch normalization on the samples independently for each GPU. They first verified their method by linear classification on frozen features. They performed unsupervised pre-training on Instagram 1 million dataset. Then they freeze the features and train a supervised linear classifier with a fully connected layer followed by softmax. The number of negatives is k in memory bank and MoCo, and is k-1 in the end-to-end. We can see that MoCo's accuracy is noticeably higher as k increases. For the momentum term, a relatively large momentum works much better than a smaller value. MoCo beats supervised counterparts in 7 downstream tasks. For the conclusion, it is meaningful for showing positive results of unsupervised learning in computer vision tasks and datasets. For future works, the authors say that the larger scale data may not be fully exploited, and also an advanced pretext task can improve the result. Lastly, it can be adopted for various pretext tasks like in language build and so on. Thank you for listening to this presentation, and this is the end of the presentation.